I'm Elias, I'm from Linaro, and with Ivan we did a proof of concept on how we can configure switches or any other hardware for what's upcoming on Linux for TSN. TSN stands for time-sensitive networking. So as we can see, and as we know, an increasing number of vendors are adding their hardware on their hardware support TSN features, and they're adding TSN features on either single Ethernet interfaces, network interfaces, or network switches. So traditionally, what we see on the Linux kernel driver-wise is when a vendor adds a switch driver, there was no infrastructure on how to configure that switch. So every vendor used to discover a proprietary way, either that was IOCTLs or it was a netlink interface that was talking to the kernel, configuring that hardware. And this seems to be going on and on the TSN as well. As you can imagine, TSN is going to have severe security implications on the whole thing. So ideally, you'd want your code upstreamed. So you don't have the maintenance nightmare across releases, and you don't have to maintain your code and your patches across releases just for configuring your own special hardware. So until today, there was an attempt from Cisco a few years ago to propose something that could be used as an API or an infrastructure to configure TSN, but nothing was accepted at that point. And at this moment, the only feature that's remotely related to that is the CBS schedulers that's only on Intel i210 and on cpsw, which is a TI driver that Ivan fixed on that. The available solutions, that there are APIs on the kernel, and this is important to understand that at the moment there are available APIs we can use to configure that hardware, but they don't cover all the cases we need. Or to put this differently, when trying to apply it on the TI hardware we had cases that we couldn't cover configuration-wise. So we think that there are some things missing from those. So this is one example hardware that you might have. As you can see, there's two Ethernet controllers that are TSN capable, and there's another 4-port switch. So this can be any combination of what you're seeing. You might only have one Ethernet controller, or you might have 2 Ethernet controllers, or all of them present on the system, or only the switch. So the first question that comes in mind is, how do I configure all of these? Because it's probably not going to be based on the same driver. Now, as we already mentioned, there's a certain kind of interfaces that support CBS. CBS is a credit-based shaper that has hardware features on that. And at the moment, for the Intel hardware and the TI hardware, we're using IProot to configure that. So we're using IProot from the user space. We're configuring the limits and the variables we want on the scheduler, and the driver is responsible for configuring the hardware as well. So ideally, we'd like to use the same thing, because it makes sense. The infrastructure is already there, and it's a solution that has survived the Linux kernel for many, many years. So the APIs that the Linux kernel offers is switchdev and DSA. They're fundamentally different. They're trying to cover different use cases. Switchdev was actually introduced by Mellanox. DSA was an independent try to configure cascaded switches on a hardware. So once you're done with the driver, and if you do what's already there, that's important to understand that what we're trying to propose is already there on the Linux kernel API-wise. So you're going to end up with this. So this is typically an Ethernet interface on your Linux kernel, and this is how your switch is going to look like. So the API actually exposes an Ethernet interface for every switch port you have. After that, you just use what's already there, IProot, you configure the Ethernet, and this configuration is just propagating to the hardware all along. And you can configure pretty much everything you need on your hardware. So this is the basic operation. It creates as many network interfaces, so you end up having access to each port from the user space using netlink, and you can configure each interface individually. That translates to you that you can configure each port of your switch individually. Okay, this is just a reference that DSA, although it has similar functionality, the way it works is a bit weird because it reinjects packets on the network stack, and since you're trying to design a driver that's there for time-sensitive networking, and every packet has a very short time to deliver, reinjecting them isn't exactly ideal. So it should be avoided. So what you gain? Now, what you gain out of that is that you eventually end up having a common configuration plan for switches and Ethernet interfaces. So you use one tool from the user space to control every aspect of your networking hardware. And this is really easy for configuration-wise, for the orchestration that's going to be needed, or any automatic operation that you want to do and configure the interface. Every interface you have, vendor independent, it's going to have the same configuration way. Okay? Of course, every vendor will have to fix the driver, add the functionality, and add the configuration, the hardware-specific configuration you have to do to enable TSN. But from a user space point of view, this is going to be the same for everyone. So at the moment, we have a patch that's going on. It hasn't been yet accepted because there were some objection on the general design and how we enable the switchdev mode on the switch and how we use that to configure the switch. But we're still going to try to get that approved and applied. But after the patch is applied, as you can see, the first command is how you add a VLAN on the switch. So the bridge command is pretty much found on every Linux distro at the moment. And you just pick the port you want to add the VLAN. You figure out if it's going to be tagged, untagged, or whatever you want to do. And after that, you can apply the TC command is applying the Q discipline. So by using what's already there, you can configure your whole hardware. And the only thing that's needed is to make the driver use the model that the kernel offers. So the future plans after that is, as I said, we're still going to try and push along and try to make the switchdev API work on the TI driver and get accepted. After that, there was a very interesting, TSN is way more than configuration. The configuration part is just the entry point on how do I enable the whole thing on my architecture. So the next logical step is Intel proposed TAPRIO, which stands for time-aware scheduling priority. So it's, at the moment, TAPRIO is a software scheduler that implements the IEEE QBV scheduler for TSN, and it's strictly a software implementation at the moment. But this is going to be extended to hardware, so you're going to be able to configure your hardware as well. The first thing we need to do is get involved and contribute on that as well. The ETF is another interesting feature. It's actually telling the hardware exactly when to send the packets on the network. So it offers greater granularity on top of QBV scheduler, but no one is even certain if it's going to be used at the moment. And the last thing we are trying to do is that on the measurements Ivan is going to present in a bit, you'll see that the Linux kernel's network stack is not even close in doing what TSN wants. So you're talking about, in specific cases, you're talking about under a microsecond of latency, and Linux kernel does around 70 at the moment. So this is really far away from what they're trying to achieve, and there was, XDP was merged a month ago, which practically offers an offload from the hardware to the user space, to a user space socket. So we did some measurements, and on a very draft initial idea and a proof of concept we reached almost 2 microseconds from the hardware to the user space. So this is looking promising for TSN implementations, but this is one of the things we want to look at. Okay, now, Ivan did the tests on the hardware we had, and we just used the whole patch we presented to prove that you can configure the hardware from user space and have the same results as what the independent code from TI was doing at the moment.
Hi, I'm Milan Hanzhuk, and I'm CNE from Texas Instruments. And now I'm just going to show you several plots and measurement results we've got when done some tests for CBS shaping and for latency measurements for Linux kernel stack. So first of all, let's describe measurement approach we used for that. For that we used hardware timestamps that can be get as on RX as on TX side using high resolution PHC counter. This PHC counter actually generates timestamps when packet leaves and received on the line. And in our case, in our hardware, we have a hardware filter that actually get these timestamps only for PTP packets, both as for L2 as for L4. So using this approach, we can fastly test with only one board as latencies as interchannel impact. And I'm just going to show you how we did this actually. So we can get complete latency from application to the wire, from the wire to application, but for this we need to synchronize PHC counter with system counter. And this is done with phi to sys daemon that from a Linux PTP packet. Also we can break down this to latency that packet spent in the stack, in the packet scheduler, VLAN layer, and NIC driver separately. Also, that allows us to measure network round trip latency. And even with this case, we just measured speed. And we can measure speed actually even for several packets because we use only hardware timestamps. And that's eliminate a software impact of driver and operating system. Also, we can observe how Shaper works. We can see on timeline how actually it puts packets on the line in those timestamps. And last thing that we actually measured with this is interclass interchannel impact when we have several channels on the Ethernet card. In our case, it's class A and class B. And with this pirate between packets, when we send one packet, then second, then third one, we can measure time between those time pirate between those two packets and see how actually one channel impacts on one on another. Yeah. So we have a lot of measurements, but I'm just gonna show you several ones that we've done recently. And at the end of the presentation, you have a link that can be used to look on all of them. This is layers latency impact. A black one is a complete latency. About maximum, worst case, 50 microseconds. This is not RT kernel, this regular kernel without any optimization, without any CPU pinning, just one channel, class A, CBS shaper preconfigured, and we are sending packets from application with speed 100 PPS. And compared with the measurements we actually have done recently for that and presented in last Connect, we used VLAN layer that added us 3 microseconds more, about 3 microseconds more. That's actually not very well, but in our case it doesn't work in another way because we have hardware that don't have VLAN offload. So this is for this test we need to synchronize actually PHC counter with system counter to both those counters to be on the same timeline. Then we can extract them and measure latency. And with this we can investigate actually a latency in the driver. So it's one of the on the plots, but we have much more, including dispersion of this latency, just a little bit different. I expected that here would be one more picture. So also we can investigate interchannel impact, but in this case we don't need any synchronization. We used only PHC counter that in our case has resolution about 4 nanoseconds. It's like an integrated characteristic that just includes hardware and software impact. So here, three histograms. One is for class hardware class A. Second one is for hardware class A, and in parallel we have class B. And third one is when we have class A and in parallel class B and best effort traffic. And this is inter-packet time dispersion for this. And those diagrams actually, histograms actually show us that there is no difference between class A if we apply some in parallel class B. Here we have speed of class A about 40 megabits. Why 40 megabits? Because it allows us to get paired between packets with 100 microseconds. That allows us to eliminate actually packet spans in the software stack. So we have enough time to packet reach this hardware CBS shaper and observe actually how CBS shaper shapes the traffic and how one channel impacts on another. This is for class A, and same test case absolutely for class B that is running in parallel. As analytical sum value, we can compare actually root mean square for those two pictures. That is in case when we applied some best effort traffic, changed a little in 10 times, but it's in normal peak-to-peak ranges. Also, we did some comparison of software and hardware CBS shaper. Actually, software CBS shaper implementation is applied on Linux kernel now, and hardware CBS shaping for TI is also there, so we can compare them. And here, even without any explanations, we can see that dispersion of the pirate of packets greatly different. And if we compare root mean square, we can see that it differs in more than 100 times. And this is the same test, but we applied best effort in parallel. Best effort here only 40 megabits because it has huge impact actually when we use all bandwidths. So for comparison, we can see that software CBS shaping is much hardware CBS shaping is much better than software. Red one is for class B, black for class A. So this is one of the examples we can use for testing actually switch approach when we have switch applied with CBS shaping. In this case, we have pre-configured CBS shaper on port 2 for 80 megabits per second. That includes speed from one board and from host. So when we send some traffic from big and small black, like for class A, 40 megabits, and shape the traffic on port 2, and in the same time we send class A from host side, because IM572 can be in switch mode, and it has like 3 ports, 1 for host and 2 external ports. Using these hardware timestamps, we can observe actually how CBS shaper works itself. The main advantage of this method is that we eliminate actually software impact when we have 2 parallel streams from the same CPU. Actually, we have a lot of measurements, and we used a self-written tool to get those results. Here links where you can see on them, and PLJet is a simple tool, and you can see how we configured those shaping, configured timestamping documentation, how to configure shapers actually in the kernel now. You can read it. CBS tests, all tests we've done at this moment, and TSN latencies is all data we get, plus scripts to build GNU plot plots. So, and next one is just to allow on cpsw driver belong hardware timestamping because it was not initially applied. So that's it.
All right. Any questions?
So for the testing you just did on the CBS stuff, do you guys consider trying to do something similar, but instead of running the packets through the Linux kernel's traffic shaper, make a DBK ODP application that does the shaping and keep it all in user space?
We did the measurements with XDP, but the problem with the XDP is that they don't use the socket functionality about timestamping, so we couldn't use what was already there. So we kind of hacked it. When a packet arrived, I just replaced the last 64 bytes with the timestamp counter, and then I get the same timestamp counter from the user space and figure out how much time it takes for the packet to traverse the whole thing. We could do something similar on DPDK, because we don't really care about we just need to know how much time the packet takes from the hardware to the user space. So we can just hack the packet, replace the last 64 bytes, add the TSC on that, the timestamp counter, and do the same. It's fairly fast and fairly easy to figure out how much time it takes. On even running a scheduler on top of that, so you just get the time that you need. Yes. This is on the plans to do. I'm trying to figure out a way on how to standardize those measurements on non-socket APIs. Because on the socket API, you just have the timestamp on the socket, and this is what the tool does. So we're trying to standardize it somehow, but there's mostly ugly hacks at the moment that we're using on the driver and the user space to figure out how much time we need on that. Anyone else? Right. Thank you very much.